Okay, let's start there. You put a couple of aspirin tablets in a cup of water, dissolve them. What's the pH?
Oh, that's like a real life situation.
Yeah.
That's crazy. No, I was just gonna call it
C9H7O4. HC9. My 9 kind of looks like a 7, my 4 kind of looks like a 9, but that's just me.
Where did it go?
What do y'all get for molecular weight, Fasper?
180.
Got 180?
Yeah.
I'm hoping we're not gonna have to use the quadratic. Yeah.
I don't know what we do.
Yeah, you have two 250 mil tablets.
Oh no, we do have to use the quadratic.
Do we?
Yeah.
That sucks.
It's not smart.
Fortunately for us, I bet somebody's got a calculator that'll do the quadratic real easy. So.
Yeah, I got it. So it means I should think about it. So it's x squared over
Yeah, just gotta be less than both though.
over.
So we have aspirin, who's gonna do that, plus water goes to and we have 0.5 grams over 180 grams per mole divided by 0.24 liters, which I get like 0.116 or something like that, I think was what I saw. 1.16 molarity. Well, 116? Oh, sorry.
Yeah.
116. 0, 0. That right there tells me that I probably should have put 4 tablets in there. X, X, and X. So 3.3 times 10 to the minus fourth equals x squared over 0.0116 minus x. And I've already heard that we're not going to be able to drop it, so I'm going to go ahead and not drop it. So what do we have here? So 3.3 times to the minus 4 times 0.0116 is what? This times that.
Oh,
And now the 6 times 10 to the negative 6.
It's what?
3.86 times 10 to the negative 6.
So 3.86 times 10 to the minus 6th minus 3.3 times 10 to the minus 4th x equals x squared. So x squared plus 3.3 times 10 to the minus 4th x minus 3.86 times 10 to the minus 6th equals 0. So A is 1, B is that, C is that, and plug it in the quadratic equation, right? So somebody probably has a calculator that has quadratic preloaded on their calculator. So what do we get for x? 0.0018. Okay. Now, Alex, is that right? Alex over there did not do the quadratic, and he got 0.0020. So you can see that even though you needed to use the quadratic, not using the quadratic was not a huge disaster because you were close, right? So we're starting to see deviation, but we're not seeing tons of it yet. But there have been problems like in the homework where if you don't use the quadratic equation, you end up getting you get wild numbers, like you have 0.5 molar starting solution and you need to use 720 moles of it. It's like, that doesn't make any sense because you don't have 720 moles. All right, so, all right. Well, we solved for x. That's not the question. What's the question? What's pH? So what is pH?
2.7.
2.7?
Yeah.
Okay, awesome. So we have a 2.7 pH. So this is my H3O plus. So my pH is 2.7. All right. So this will be A. So B, how much sodium salicylate must you add I don't want a pH 2.7. That sounds like it's going to like eat a hole through the lining of my stomach if I keep doing that. So I want pH 4. I'm going to add some sodium acetyl salicylate. This was done like 75 years ago and has been commercially available since then on the aspirin aisle. Does anybody know what the brand name of that particular aspirin is called?
That one? Wait.
The one that has, when you add acetyl salicylic acid and sodium acetyl salicylate, what have you just made? What do we call that generically? What is that called? When you have a weak acid and its conjugate base, what do we call that?
Buffer.
A buffer.
Yeah.
I wonder
Sodium
what that's
tablets?
called on the aisle.
With the Advil?
Buffer.
Bufferin.
Oh, that's horrible.
Right?
Well, I guess I've never
Bufferin
used it.
is the aspirin that has a buffer in it. So
Wow,
it's
people,
not so acidic.
people are so creative.
Buffers. Advil is actually a totally different compound. So.
Oh, wow.
Yeah, Advil's ibuprofen.
Right. And ibuprofen is similar in structure but different. It's not acidic for one thing. So to do this one, still the same reaction. This is still 0.0116, but that's my X. How much sodium whatever, that compound. How much that we gonna add? And we want this to be pH 4. So I know that number. So that means this has to be 10 to the minus 4. And this has to be plus 10 to the minus 4. And this has to be minus 10 to the minus 4. Right? Because of 1 to 1 to 1 to 1. Yes?
Do you not put an X under either?
Do I what?
Do you not put an X under H3O?
No. Oh, here?
Yes.
Well, normally I start with 0, right? And if I don't have a buffer, both of them are 0. Right? If I'm over here, starts at 0, because I haven't started breaking it up yet. But before this reaction starts, this is 0 because I haven't started breaking it up yet. But this is not 0 because I actually added some sodium acetals, that compound. Right? Well, so 3.3 times 10 to the minus 4th equals X plus 10 to the minus 4th times 10 to the minus 4th over 0.0116 minus 10 to the minus 4th. 1, 2, 3, 4. So I'm going to be able to drop that number. So if X is a lot bigger than 10 to the minus 4th, then I can drop both of those. Right? I know it's small relative to this one because that would make that 0.00115, and that's not going to change. Okay, so I don't know, what's X? Looks to be like about 0.04, 0.038. Okay.
Oh yeah, that's
So 0.038 moles per liter is X moles over 0.24 liters. So X is something.
0.0092.
Okay, so you told me this weighed 180, right? I'm going to take off that H and replace it with an Na. So I'm taking off 1 and adding 23, so it's going to have a weight of 202.
Yep.
Right? Because I'm taking off 1 and adding 23. Okay,
Sure, yeah.
so 202 grams per mole. Whatever that is.
1.86.
1.86?
Yeah.
Okay. That's a lot. Okay. So, I have to add 1.86 grams of sodium acetylsalicylate to my half a gram of aspirin to get a pH 4. Yes? To sodium acetylsalicylate?
Yeah.
When you make sodium acetylsalicylate, this is acetylsalicylate, So sodium acetyl salicylate would be that. Take off the H, replace it with an A. Right? Which technically I could have just started from scratch and added it all up again, but I already knew one was 180, so it was easier just to subtract one and add 23. But I could have taken 23 plus 9 times 12 plus 7 plus 4 times 16 and got the same number. Okay. So that is a buffer. So to make that buffer, I have a half a gram of aspirin, and I have 1.86 grams of acetyl salicylate. Could I make that buffer? Oh, let's do this. Okay, so we got our buffer now. So now we have our buffer, so let's do C. What is the pH buffer after adding 10 mils of 0.005 molar? Let's add some ACL to it. There we go. So let's do some question analysis before we get into the math. Just non-mathematically, if I look at my original equation, which is my governing equation for this whole thing, right? If I add HCl to this equation, Le Chatelier says the reaction is going to shift which way? What's the HCl going to react with?
The column.
Which side am I adding acid to?
The products.
The acid's on the product side, right? They're both here in equilibrium.
Yeah.
Everything's there. Products and reactants are both there. If I add HCl, I'm adding H3O plus, right?
Yeah.
So I'm shifting the reaction that way,
Amen.
towards reactants. What would water do? I added this. It's going to flow downhill that way, right? Because that's what I added. Because HCl is H3O plus and Cl minus, and Cl minus is irrelevant. So we're adding H3O plus. Yes? I gotta speak up. What? Why what? Why did I add it? I don't know why I added it. I mean, I'm just saying, it's a buffer. I want to see what's going to happen to the pH when I add that acid. What is going to happen to the pH? I mean, the reason why you have buffers is so the pH doesn't change. That's the whole goal, is to keep the pH relatively the same. If you ever have a relative who's in ICU, the way you know they're about to die is because their blood pH steadily changes. If their blood pH starts to change, you know that they're about to die. Because it's that important to keep that. But think about it. You're breathing out CO2, which is an acidic gas. But yet your pH doesn't change on your blood because your blood is buffered. Right? Okay. So how much H3O plus did we have? How much is that? How many moles is that? 0.00005?
Yeah, 5 to the negative 5 times 10 to the negative.
Okay. So I have this reaction. So it's going to react with this stuff and go this way. Okay? That's what's happening.
Yeah.
Okay? So I just added 0.00005, something like that. And I have 0.0092. So Chem 1, what's my limiting reactant?
Yeah. H3O.
Can you see it's the H3O plus?
Yeah.
Which means it's all gone. Probably should have added a little bit stronger stuff, but whatever. Okay, so I don't have any of that left over. I have 0.00915 left. Those are my starting numbers. I have, this is, okay, so my initial acetylate is 0.0116 plus 0.00005. I'm not really very impressed by that number, but whatever. This number is that one, 0.00915. And then that's 0, and then like normal. So when you do a titration, when you add acid or base to a buffer, you do that second reaction over there, do the Chem 1, what's the limiting reactant, to figure out how much of that stuff goes away, and add and subtract that to your regular acid-base equation, and then give yourself, figure out what it is. Okay, so here we go. Let's do it. So what do we have? 3.3 times 10 to the minus 4th is still that, is equal to x times 0.00915 plus x over 0.01165 minus x. So if x, hopefully this is going to work, if x is small relative to 0.00915, then we can drop these x's. I don't know, let's see if we can. I think we can in this case. I think it works. So what do we get for x? I don't know, maybe not. Maybe I can't drop it. I may have to use quadratic again, at which point I'll really hate myself.
Oh no, it's small. It's 4.2 times 10 to the negative 4th.
4.2 times 10 to the minus 4, which is less than 9.15 times 10 to the minus 4th, so we're okay. Okay, cool. I don't want to have to do the quadratic twice in a row. All right. So, what's my pH?
3.4.
3.4. Yes.
I still don't understand why it's 5 to the negative bit from H3O when we had an H6. I don't understand the thought process behind
You don't understand why it's 5 times 10 to the minus 5th H3O?
it. Yeah.
0.005 moles per 1 liter is X moles over 0.01 liters.
No, I get that. I don't know why those two affect each other. I don't know why H3O and HCl have anything to do with each other.
You mean H3O and the ion here?
No, because we added hydrochloric acid to the
Yes.
buffer, and I don't understand why.
The hydrochloric acid, this is the hydrochloric acid right here. Because HCl plus H2O goes to H3O plus Cl minus. This number is right there. That's what's reacting with this ion, this Bronsted-Lowry base. So this acid I just added reacts with that Bronsted-Lowry base to give me the unionized acid and water. But since this is being added, it all reacts because I got an excess base here. So this all reacts. Once this reaction is done, now I come over and find out with my new numbers of what I have now in my beaker, how much of that and how much of this, how much acid and conjugate base, what would the pH be? Does that make sense? Okay. So notice even after I added 10 mils of acid, my pH only went down by 0.6 pH units, right? So it stayed relatively the same. And that's what you notice with buffers, is it'll stay relatively the same, stay relatively the same, stay relatively the same, and then it's going to suddenly start spiking. What is going to happen that's going to make it start spiking? Just from an algebra standpoint, what's going to make it start spiking?
It overcomes the buffer.
When this number I'm adding and subtracting becomes significant to the numbers I started with.
Yeah.
At that point, the whole idea that I could drop it is not working anymore, right? And so you have what's called buffer capacity, which is how much stuff, how much acid or base you can add before, in common terminology, you blow your buffer out. But before the amount of acid and base you're adding becomes significant to the amount you started with. Because remember, to make a buffer, you have an acid and a conjugate base, right? Mm-hmm. If I have, let's say I'm 0.5 molar acid, 0.5 molar base, and I add 0.4 molar acid. Wow. Now I've really changed these numbers. These aren't 0.5 and 0.5, they're now 0.1 and 0.9. Yeah. That's a really different number now. On the other hand, if I go 0.5 and 0.5 and I say, okay, well, let's adjust that number by 5 times 10 to the minus fifth, still 0.5 and 0.5. So I'm gonna get the same pH. You see how it works? Mm. And so that determines what your buffer capacity is. So if you put in some acid, you find out, oh, the pH has started to really spike. What could you do to solve that problem? What's the solution? You've blown past your buffer capacity. It's not acting like a buffer anymore. You've totally screwed it up. What can you do?
Common ion effect?
Well, yes, the common ion effect is always there, but what can you do to the buffer?
Add more buffer.
The reason why you blew out your buffer was because the number of moles of acid and base you added started to become significant to your starting values, right?
Yeah.
Oh.
Increase your starting values.
Yeah. So add more buffer.
Make these two numbers bigger,
Okay, cool.
right?
Yeah.
If you say to the average college student, hey, I'm taking $10 from you, and you're like, man, hey, that hurt.
Yeah.
If you say the same thing to Bill Gates, he's like, what? Huh? I didn't notice. Right? Because it's not important to him. It's more important to me, because that's like a pizza or something. You know, I gotta go get half a pizza these days.
Oh, yeah, we charge way more.
Okay, so,
3/4
Yeah.
of
so what can you do? Increase the capacity of your buffer,
Yeah.
right? Increase the molarity of your buffer. Now, this becomes a real issue in biochemistry. A lot of your biology majors, biology, biochemistry, when you start doing that, because you increase the amount of buffer, you increase the amount of salt in the solution, because you're also increasing the amount of sodium and stuff too. And you can start to get things to where your enzymes go, ooh, that's too much salt, let's unfold. And then they don't work anymore. So you have real issues with how strong can you make the buffer, which means you have to be really careful as to how much stuff you add. Now, where is the best place to have a buffer? Now, what's a buffer supposed to do? Let's go through this again. What's a buffer supposed to do?
Make it so that the pH doesn't want to change.
Make it so the pH doesn't want to change. So it doesn't change if I add an acid, it doesn't change if I add a base. It doesn't change. Okay? So where's the best place to have a buffer?
Neutral.
No,
What,
not really.
what was it, like the value you wanted to have?
Yeah. The best place to have a buffer would be where my pool of acid and base are the same size. And then I don't care. You had acid, great. You had base, great.
Oh, yeah.
That's got the most wobble room, right? Because I can add acid and base and not screw it up.
Yeah.
Okay, well we've talked about that before. What do we call the point where we have equal amounts of acid and base, conjugate base, in our solution?
Equilibrium.
Yeah.
Well, no, we're always at equilibrium. But look at our equation there. If I have the same amount of acid as conjugate base, what happens to this equation? What would happen to this equation if that number was also 0.0116?
Cancel out.
Everything would cancel out, right?
Yeah.
And when this and that all cancels out, where are we at?
pH equals
We're where?
Half equivalent.
Half equivalence point.
Yeah.
We're at the half equivalence point. Because the half equivalence point is where we've turned half of it into conjugate base, right? And so these numbers are the same.
Yeah.
So the best place to have a buffer is at the half equivalence point. And tell me about the half equivalence point. How do I know when I'm at the half equivalence point?
pH equals pKa.
The pH equals pKa. So where's the best pH to have your buffer?
By pKa.
At pKa. Which is why you have tables of pKa values. Because they'll tell you where's the best, that's the best buffer for what's going on. So, you want to make a pH 9 buffer. Okay? And you go look on a chart. And you find out that you have here's a pKa chart. And you got an 8.6, and you got a 7.2, and you got a 9.3, and you got a 9.1. Which one of these acids should you use to make your buffer?
The 9.1.
The 9.1, because it's closest to the pH you're looking for.
Yeah.
Unless there's some other issue. Like, this is a biochemistry thing. And this is,
Yeah.
okay, so you gotta look at the other part, it's like, okay, yeah, from a pH standpoint, this is the one I want, but I really don't wanna put arsenic in with my enzyme, that's a bad thing, okay? So I'm not gonna use that one because I don't wanna kill my enzyme, right? So, it's not the only thing to look at, but it is a thing to look at, right? So from a pH standpoint, 9.1 is awesome. There are other factors, It's like I can make a really good sunscreen that's made out of nanoparticle platinum.
Yay.
Works really well. But,
You're covered in heavy metals.
well, first, we're covered in heavy metals. Secondly, we're talking like $10,000 to slather yourself with this sunscreen. So, there are other issues to take into account. It's like, yeah, it does a great job, and if you're the Sultan of Brunei, fine, go use nanoparticle. But the rest of us have to find something cheaper. Okay, so. Okay, got it? Typically, if you think about these numbers here, if let's take a real easy one here, so we can let's start with an easy one. So let's say we have a pKa equal to 5. Okay? So the best place to have my buffer, if I have 10 to the minus 5 here, is equal to my A minus times 10 to the minus 5 over my HA. Right? HA goes to, plus water goes to A minus plus HA plus H2O goes to A minus plus H3O. Right?
Yeah.
So if I want to be pH 5, and it's got a pKa of 10 to the minus 5, or it's got a Ka, it's got a pKa of 5, then my A and HA have got to be the same.
Yeah.
Right? But what if this is pH, what if it's pH 4? Now what's the relationship?
You need more HA. Right? Wait.
What's my HA to A ratio now?
Yeah.
HA over A, hold that over here, right, is equal to 10 to the minus 4 over 10 to the minus 5, which is
1 over 10. Or 10.
10 to 1,
10 over 1.
right?
Yeah.
Okay.
10 is
What if I wanted it to be pH 3?
100 over 1.
It'd be 100 to 1, right? And remember what a buffer does? It has to resist pH change going both directions.
Yeah.
And if I got 100 times more of one than the other, it's not very good going towards the smaller side. It's awesome going that way, but it's horrible going this other way.
Yeah.
Right? And so the punchline is you want your buffer to be 1 pH unit, within 1 pH unit of pKa. Because a 10 to 1 ratio is really about as big as you can have and still have it act as a buffer. If it gets bigger than 10 to 1, it's pretty much not buffering. Or it's not buffering, it's only buffering one way. Now I say that, and then immediately the buffer in the carbonate buffer in your bloodstream has a pKa of 6.2. So some of you pre-med types, what's the pH of blood? Anybody know? No? 7.4. That makes it a pretty crappy buffer. Actually, it makes it an awesome buffer as long as you only go towards the big side, which is the acid side.
Yeah.
And everything that you eat, drink, and breathe is acidic. And so your blood doesn't care that it's a crappy buffer against bases, because if you drink Drano, you deserve what you get. Okay? And so it doesn't matter about, because everything that's going on metabolism-wise is acidic.
Yeah.
And so, yeah, it's not optimized as a carbonate buffer for both acid and base, but
Pretty good for us.
bases aren't really relevant because we don't have many basic things that we are experience or get in our bloodstream. Okay? All right.
Yeah, every day.
So
To wake me up.
So that's what a buffer is. Okay? Now there's another thing, I'm pretty sure we talked about this, but I just want to go back and make sure. Indicators. There are a lot of compounds that change colors when the pH changes. Good example, fruit. right? You got an orange. It's green when it's not ripe, when it's and if you, or say an apple, because we grow apple trees, we have apple trees around here. You eat an apple that is not ripe, and it is so sour, so bitter, just like, ew, why am I eating this? Because it has a very low pH, it's very acidic, and it's green. However, as it ripens, those acidic compounds get turned into sugar, and the pH goes up. And the compound in the rind of the apple goes to get red, because the pH change went from very acidic to more basic, and it changed color. And you see that on most fruits. Most fruits have a high pH, low pH change. That's a signal that tells the birds, hey, come eat my fruit now and spread my seeds all over the place. Okay? Because that's why they have fruit in the first place, right? So animals will eat it and go wander off and poop the seed somewhere else, fertilize it, and have it ready to go on a new plant, whatever it is. Okay? Flowers, same way. Flowers, when they bloom, the pH changes and they go from green or white or whatever it is they are to a different color because the pH changed. Okay, so these indicators, pH indicators, are all just compounds. They're isolated compounds from the natural environment. Litmus, for example, comes from a moss that grows, a cave moss that grows somewhere. It's so ubiquitously used that now we figured out how to make E. coli do it, but it was originally extracted from some cave moss or another. Those compounds tell you when you got to a specific pH. So if you have, so let's say we have a compound that goes, if it's acidic, it's red, and if it's basic, it's yellow. Okay? So we have, this would be our acidic. So this would be our red. This would be our yellow. So if we're at the pKa of that indicator, where are we? What color are we at?
Orange.
We're orange. Because I have equal moles of red and yellow. And so what happens is, if you have a pH indicator that goes from red to yellow, it'll start red because it's in the acidic form. You're going to add base. It's going to go red, 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 getting kind of orangey, 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 yellow. And so typically when you're looking at an indicator, a pH indicator, you do the same thing you did with buffers. So, for example, the phenolphthalein indicator, which you guys used in lab. The phenolphthalein indicator has a pKa of 9, which means that you're going to start seeing color at 8, and it's going to be super pink at 10. Because 8's where you're going to start seeing a little bit of color bleed in, because you're going to get a 10% of it's going to be in the red form. And by the time you're over at 10, it's pretty much all in the red form and none of it's in the colorless form, right? And so when I was doing lab, because I'm red-green colorblind, people come up and say, is it done? Which is the wrong thing to ask for a red-green colorblind person. But, hey, is it done? And my answer is, do you see red? And they'd say, yes. I'd say, well, it's done. I don't see it. But if I see it, you're way past 9. You're somewhere out here at 10 or 11. And that's why whenever you're doing a titration, they say, what's the drop you saw the color? That's what they want to know, because it just measures that one pH. Any number above that, it's just going to get more intensely whatever that color is. So, I have people in lab who come in and let's say the pH is going to hit that pH 9 or pH 8 at, 10 mils. And they'll come in and they'll say, I've added 65 mils and it's still pink. Well, yeah. And if you add 65 million mils, it'll still be pink because you're on the pink side. I don't care how much you add, you just get pinker. That's all that's going to happen, right?
That's also.
I guess if you add enough, you'll dilute it down to where you can't see it anymore, but we're talking oceans of stuff. Okay, so. Let's take this stuff right here. What kind of a pH indicator do I want to use for that aspirin? Not the name of one, because you don't know the names of them. But I want a pH indicator that has what properties? What properties do I want it to have?
Changes color at pH 4.
We know that the half equivalence point is at 4, right? Because we calculated that earlier, where the pKa we found out was 4. So ideally, we want a buffer, we want an indicator that changes at 4. Okay, what if we use phenolphthalein in this solution? That would be a bad idea because we hit the end point of the reaction at 4, but the color doesn't change until we get to 9.
We should use methyl orange.
So that's not good. And so if you take a look, you can go out to Google and find them. I'm sure that's what you just did. Yeah, you can go out and find, there are, I don't know, 500-600 indicators out there. And you can basically say, I need a pH indicator that's 3.2. Somebody's got one. You know, sometimes you're going like, 3.2, that's gonna cost me $50. But I got one that's 3.5 that I've already got. So I'm gonna use that one. Because, it's not that one. But I wouldn't want to use one that's 9 or 10. I wouldn't want to use one that's 1. My favorite indicator is dynamite.
Congo red would work.
Dynamite is actually a pH indicator for pH 13 or something like that. So it's like nothing like it. Let's take a stick of dynamite and let's put it in Drano and see what happens. The color will change. It'll probably blow up too. But,
That's the fun part.
that's right.
That's besides the
All right. Okay, guys. Have a great Thanksgiving. I will see you guys in a week and a some.